Hi, welcome back to Statistics 1. We're in the second segment of the first lecture. Last segment we talked about the power of randomized experiments. I want to contrast that now with observational studies. Observational studies are also useful in psychology and in social sciences, behavioral sciences in general, but they lack the power of randomized experiments, and I'd like to show you exactly why. So the important concepts to take away from observational studies is I'll make this distinction between a study and an experiment. An experiment is when we have random assignment to conditions and something is manipulated in an independent variable. Studies are observational studies in particular. We're just going to go out and measure a bunch of things. Nothing is manipulated. One large class of observational studies that exists, particularly in psychology, are studies where we're looking at patterns of correlations among lots of measures. And that can be useful, but again, it lacks the power of randomized experiments. I'll then describe what I call a quasi-independent variable. It looks like an independent variable, but don't let it fool you. It's not a true independent variable. So I'm going to talk about two examples in this segment. The first example is the field of intelligence testing. And then I'll take a very specific example. Some research that's going on here at Princeton University that I'm involved in is the effects of concussion on the brain and on cognitive performance. So this first example is intelligence testing. And this is sort of meant to be a joke, but when you look at the history of this, it's actually true that standardized intelligence testing sort of hit the United States around the same time and at even stronger rates than polio. Unfortunately for U.S. children, and we have lots of models of intelligence, but unfortunately for U.S. children, we have not eradicated standardized intelligence tests. They're still administered and probably at stronger rates today than ever, and it's not clear why we're still doing that. What happens in these studies of intelligence is I refer to these as studies because nothing's manipulated. All we do is administer multiple tests or multiple items within tests to lots of children. And then we examine the patterns of correlations among those items and among those tests to come up with some theory of the structure of intelligence. And the first psychologist to do that was Charles Spearman in 1904. He actually looked at scores of children's scores in 6 different disciplines in school and looked at the correlations among their scores in those different disciplines. And from the pattern of correlations, he developed a model of intelligence. And this is an example of what Spearman's model looked like. Spearman saw that scores across all the different disciplines, and these disciplines were very different. There were math and English. There's even music, and it was one of the classes. Across all the different variables that he measured, so these are the variables down at the bottom, there were positive correlations among all those variables, suggesting to Spearman that there must be a general intelligence. There must be some single factor that caused all those positive correlations. And that's what led to this notion of general intelligence, the fact that there are positive correlations among all the different grades and all the different classes among these school children. That's one model of intelligence. Other people came along and said, hey, wait, the patterns of correlations are actually more complex than that. If you look at lots of different kinds of tests. So if you look at lots of mathematical tests and lots of verbal tests and so on, you start to get something that looks more like this, where you have multiple factors. So F1, F2, F3, there are multiple factors. So this could be, say, this could be verbal ability, this could be spatial ability, and so on. And there's actually multiple intelligences. And this type of model of intelligence was advocated by Thurstone as a challenge to Spearman. It turns out that that type of model doesn't work very well because those second-order factors are correlated themselves. So you still need to incorporate this idea of a general factor. So this has led people to propose this kind of structure, which is known as a hierarchical structure, where there's still this general factor or general intelligence, meaning that some people are just smarter than others. There's some general source of variance underlying that. Yet another way to depict that is this way. So there's some general factor that influences all sorts of tests, and then there are more specific factors that can also influence those tests. So you might be just generally smart, whatever that is, but you might be sort of poor in spatial ability and really good in verbal ability, and each of those will independently influence how well you do in school in those particular disciplines. The problem is that these observational studies, there were no manipulations of an independent variable, so it's impossible to make any claims about causality. And this leads to the sort of classic line that you've probably heard before is correlation does not imply causation. And that's exactly the problem with this whole field of intelligence testing, is while it's rather brilliant in its ways of modeling the structure and pattern of correlations, it's very poor in coming up with arguments about causality. And that's why to this day there's still a debate about what that general factor really means, because unlike polio, we couldn't get right to the heart of the matter. We couldn't get at the causal mechanism just by doing correlations and correlations and correlations. So that's why these observational studies aren't as powerful as randomized experiments. Let's move to a slightly different example and slightly different kind of study design. This one looks more like a randomized experiment, so it can trick you. And that's why I want to start out by pointing this out so that you're not fooled by it. So one example is the effect of concussion. And here I'm going to talk about just sports-related concussion. So there's also a lot of research on just head trauma and how that can affect the brain and cognitive performance and just behavior generally. But here in the US, and actually here at Princeton University, there's a big study going on looking at the effect of sports-related concussion, particularly among football players, and how it affects, or how it can cause neural damage and cognitive deficits. So here's what the study design looks like, and it almost looks like a randomized experiment, right? Because we have a treatment that is, some people have a concussion, some people don't, and that's a control group. And then we have dependent variables. So we could measure some neural markers. So in the study that's happening here at Princeton, after an athlete suffers a concussion, within 72 hours, we put them in an MRI machine and we get measures of neural activity. And we also have them perform neuropsychological tests designed to measure their memory and attention. But notice that this is not a true independent variable, and throughout the course I'll refer to variables like these as quasi-independent variables, because obviously these athletes are randomly assigned to these conditions. That wouldn't be ethical. We couldn't just say, let's take half the football players and concuss them and see what happens, right? These things just happen. Some athletes, unfortunately, suffer concussions and they go into the treatment condition, and others don't, and they are in the control condition. So that brings up the question of potential confounds. When we don't have random assignment to conditions like this case, there are all sorts of possibilities for confounds. And in fact, this is truly just a correlational study. It's just a correlation between whether someone had a concussion and then things that may happen afterwards. It doesn't mean there's a causal mechanism. There could be all sorts of confounds influencing the relationship between whether someone suffered a concussion and whatever we measure after that. So for example, in the research that we're doing here on sports-related concussion, we know this to be a problem in the research, is especially among American football players, those players who suffer a concussion, they're actually more likely to have a prior history of concussions. And it could be that prior history or the cumulative effects of that prior history and the current hit or current injury that is leading to the outcomes that we're seeing in our dependent variables. Even more subtle than that, it could be that the types of football players or types of athletes who put themselves in situations that afford a strong hit that leads to a concussion, they might just have a certain personality type, they might have certain characteristics, they might be really fast and wind up in these dangerous situations. Those are really subtle possibilities that might also be correlated with who's concussed and who's not. And they might be correlated with some of our outcome measures, our dependent variables. Those are more subtle potential confounds. We don't know, and we can't know. Without randomized experiments, without random assignment to conditions, we can never really be sure. So again, the point of talking about these observational studies is again to drive home the power of those randomized experiments. And to remember that as we move forward and we start to talk about the use of statistics, I'm going to talk about a lot of different examples throughout the course. Always remember whether we're dealing with a true independent variable and a randomized experiment, or whether we're just dealing with observational studies and the analysis of correlations. It's not to say that these types of studies aren't worth doing. Obviously, we want to look at the effects of concussion. Obviously, we want to understand the structure of intelligence. All I'm saying is the arguments that we can make about causality are weaker in these latter types of studies than they are in the former. So again, just remember the difference between a true independent variable and a quasi-independent variable. So the important concepts to take away from this second segment is know that when I make this distinction in my language between a study and an experiment, that means I'm making a distinction between an observational type of study versus a true experimental design. And within these observational studies, a lot can be done by looking at patterns of correlations. And we'll talk about correlations early on in the semester or early on in this course, and know the distinction between a true independent variable and a quasi-independent variable.